So for this case, we consider the E field generated by an infinitely long cylindrical plastic rod. Well, yeah. Just now, a student asked me a question. What is the difference between the conductor and the insulator? So for conductor, I just tell you that the charge should always be on the surface. No matter if it's positive or negative. This is dot. Okay. But it doesn't really matter whether it is positive or negative. And the other point is that the E field inside the conductor should be zero. The E field should be zero. For the static case. So this is for the conductor. You need to consider this property. So for the insulator, like a plastic insulator, the charge can be distributed inside. This can be distributed inside. And the E inside the insulator is not necessarily zero. It can be a positive or negative value inside the insulator. And of course, so not mentioning the outside. The outside, even for conductor, can be positive or negative, depending on the polarity of the charge. But actually, when we consider what is happening inside the conductor and the insulator, their main difference is like that. So here we consider infinite long cylindrical plastic rod with a uniform charge density lambda. So that this darker one is the rod with the positive charge. So to find the field at radius r, this is r. So for this case, we should use the cylindrical coordinate. If you use a spherical coordinate, it might not be a good choice. For spherical coordinate, it will have some sort of symmetrical identity, symmetrical property. So the cylindrical have a z-axis with the same direction of this rod. So you can regard this plane is the polar coordinate. So in this case, we can actually use the Gauss law. So we have epsilon naught phi, which is nothing but E times A, because over the side surface, the E should be constant because this rod is infinitely long. No matter which point it is, you will see the same charge distribute at the same with the same distribution. So when you consider this point, as the rod is infinitely long, they will see the same stuff. So the E field should be the same for each point, given that the radius is the same. So in this case, we have phi equals to EA, and Q in charge is of course when you see the cross section for the cylindrical, it's just like a rectangle, and here is the rod. So this is H, and the charge density is lambda. So the Q enclosed should be lambda h. Should be lambda h. So we have lambda h here. And the surface area of the size, so you can cut it and expand it. It will be a rectangle. It will be a rectangle. So you have a cylindrical, and then you try to cut it this way, and then you try to unroll it, then it will be something like this. So this circle will be this one. So it is 2 pi r, and this is h. So we have a h here. So the area of this Gaussian surface is 2 pi r h. 2 pi r h. So we have an area like this. So h and h can be cancelled. So it turns out to be lambda over 2 pi epsilon naught r. So it will be pretty easy. So any questions? Okay, so next one, we consider the applying the Gauss law for the planar symmetry. This case is a non-conducting sheet. Actually, I think this figure is not drawing really well. It seems like all the positive charge are distributed on the right surface, but actually it should distribute uniformly. Actually, it's going on one side, but well, yeah, actually it would be the same. Even if it is distributed for the whole volume, the answer should be the same. So in this case, it may be good enough. So now we consider thin. Also, it is thin, so we can call it one side because it is thin means the thickness is 0. And infinitely large non-conducting sheet with uniform positive charge, positive surface charge density sigma here. The charge density sigma for surface density. A sheet of thin plastic rock uniformly charged on one side and can serve as a simple model. Here's applying the Gauss law. So we have the Gauss law, and the Gaussian surface is defined as a cylindrical similar to the previous case. Yeah. So we have the cross section like this. So you can see a rectangle here, and the Q in charge should be sigma times A. A is the area of this circle. And as you can see, all the E field is perpendicular to this surface. So the net force for this side should be 0. The net force for this contributed by this side should be 0. So we only consider this one and this one. So we have EA plus EA because for the left side we have A point to the left and the E also point to the left. So we have EA for the left side, and this is the same for the right side. We have A point to the right, E point to the right. So we also have another term of EA. So this is for left, this is for right, and Q is sigma A, similar to the previous case. So here we have E. We have E equals sigma over 2 epsilon 0. It's just like what we have derived in the previous chapter. So if it can generate the E field on both sides, then we'll have a factor of 2 here. Factor of 2 here. So it really meets this one. It meets this one. So the next case is if we have two conducting plates placing close together. So suppose there we have two conducting plates which is thin and infinitely large. We assume that the surface charge density is sigma 1 on both surfaces. Actually, it's not thin. So it should have a thickness. So the charge density on both sides are all sigma 1 on both left side and right side. So the E generated by this one. You ignore this one first. If you just only consider this conducting plate, the E field generated by this conducting plate should be E plus equals to sigma 1 over 2 epsilon 0. Actually, you can just repeat using the Gauss law. You can know whether there are the factor of 2 here. And then you consider the negative charge plate and ignore this one. So you will have negative charge here, and then the E field should have the same magnitude, but the direction is reversed. For the positive plate, the E field on the left point to the left, the E field on the right point to the right. But for the negative plate, the E field on the left point to the right, the E field on the right point to the left. So after you know these two plates, when they exist independently or separately, so we will write this. And now we place them together, close together, without touching, of course without touching. We assume that they have the same amount of charge, but without touching. If you touch them together, then all the charge will be cancelled. So we only place them close together. So that we know that the positive charge and the negative charge will attract each other. So all the positive charge will go to the right side, and the negative charge will go to the left side. So now all the E field generated by this one, all the E field will go to this side, will go to the right side, and it will become 2 sigma 1 over 2 epsilon 0. And this is similar for this one. All the negative charge will go to the left side. So all the E field generated by this plate will go to the left side, and it will be double. So actually, you can imagine that for this one, the E field generated here point to the right, the E field generated by this one here also point to the right, so that they will add together. So that they will become further larger. So E plus E minus will become 2 sigma 1 over epsilon 0. So just add them together, so cancel the 2 at the denominator. And now we define the new surface charge density, sigma to be 2 sigma 1, because all the charge go to the inner surface. We call the whole structure, this is the inner surface, which means that the right surface for this plate and the left surface for this plate. So the E field generated by the parallel plate with charge, if equally charged on the both plate, with different polarity, the E field inside this area would be like this, all the way. All of them are pointing from left to right, from the positive plate to the negative plate. And this is actually what you have learned in the circuit analysis. This is actually a capacitor. And in chapter 25, you learn more about how to calculate different structure capacitor, how to calculate the capacitance, like a parallel plate capacitance, cylindrical, spherical capacitance. Any questions? Okay, let's move on. So we have a sample problem to really know more about how to calculate the E field by the parallel plate. But for this case, we have two large parallel non-conducting plate, each with a fixed uniform charge on one side. The magnitude of the surface charge density are blah blah blah, sigma plus, sigma minus, sigma plus, sigma minus. For negative charge sheet, for the electric field to the left of the sheet, and between the sheet and right to the sheet. So in this case, we can calculate E plus generate by the positive plate, by the positive plate would be sigma plus over epsilon naught 2, because this one will generate E field on both sides. So E plus will generate E field point to the left for the left side and point to the right for the right side. You can ignore this one. Pretend this one does not exist. So you can consider E plus is point to the left for the left side. E plus is point to the right for the right side. So this one you can just substitute the numbers. So it is 6.8 mu, which is 10 to minus 6 over 2 times 8.85 times 10 to minus 12. 10 to minus 12. So the answer would be 3.84 times 10 to 5 Newton per Coulomb. And for E minus, you can ignore the positive plate. Then you can see that E minus point to the right for the left side and point to the left on the right side. Okay. So you can just substitute E minus to be sigma minus over 2 epsilon naught. And you just substitute the number 4.3 mu. So it is half of the previous one. And not actually half. No, not actually half. This is 6.8. This is not 3.4. This is 4.3. So this is actually 2.43 times 10 to 5, 10 to the 5th power Newton per Coulomb. So actually EL would be E plus minus E minus. EL would be E plus minus E minus, because they have a opposite direction. this one is larger, so it will be 1.41 times 10 to the 5th power Newton per Coulomb. And for E between EB, so we will have E plus E minus, because they have the same direction, right? E plus E minus. So the answer will be 6.27 times 10 to the 5th power Newton per Coulomb. And the third case, the E field on the right side, is actually, so actually this one points to the left, this one points to the left, this one points to the right, and this one also E plus minus E minus, because well, this one and this one point to the opposite direction. So it's also 1.41. 1.41 times 10 to the 5th power Newton per Coulomb, but this one point to the right side. Any questions? Okay. So actually we have finished this one. So we consider the Gauss law in a spherical symmetric way. In chapter 21, I have told you the shell theorem. We have two different cases, and now we can explain it with the Gauss law. So the first statement for the shell theorem is that a shell of uniform charge attract and repel as a charged particle that is outside the shell, as if all the shell charge were concentrated at the center of the shell. So you can imagine if you have a sphere with a charge on it, and then you try to draw a Gaussian surface S2, which has a larger radius than the spherical itself, then the total charge, it only consider the total charge on the right side for the Gauss law. You only consider the total charge on the right side. So when you just calculate if you have a sphere which has charge uniformly distributed. So when you use the Gauss law and you imagine a Gaussian surface which has a larger radius than it, so this radius is small r. We don't really care about how large it is. We only need to consider r is larger than this radius, then it will be fine. So using the Gauss law, we have epsilon naught integration of E dot dA equals to the Q enclosed. So actually we only consider the total charge here. So it will be actually the same as we don't have this shell. All the charge are distributed here. So on the right side, it will actually be the same. So when the right side be the same, then the left side should be the same. This one is constant, it never changes. So which means that this integration, which is the electric flux, should be the same. And now we know that the charge is uniformly distributed, which means that the E field should be uniform over the Gaussian surface, which means that this one turns out to be E times 4 pi r squared. And then you just rearrange it, then it will be E equals to K, which is 1 over 4 pi epsilon naught, and you have Q enclosed over R squared, somehow like this. So it doesn't really matter if the point charge is distributed here or uniformly distributed outside. So this is what the first statement of the shell theorem tells you. And for the next one, if a charged particle is located inside a shell of uniformly charged. So now we can ignore the outer one. And now we only draw a Gaussian surface inside it. So the Q enclosed is 0. Which means that the right side should be 0, which means that the left side should also be 0. And as long as the charges are distributed uniformly, so the E field on this Gaussian surface should also be uniformly. So it can be something like a positive plus a negative number to turns out to be a 0. It should all the way to be 0 on this Gaussian surface for EDA. Then all should be 0, also be 0. DA is not 0, so E should be 0. So there should be no E field inside this one. So E should be 0, or R is smaller than capital R, which is the radius of the sphere. So this is what the shell theorem tells you in chapter 21, and here we can use the Gauss law to explain why. So now if we consider a insulator sphere, which means that the charge may not necessarily distribute on the surface. Just now I mentioned. For insulator, the charge can be distributed inside the volume, inside the whole shape. So now we assume the simplest case, which is the charge is uniformly distributed in the sphere. So we have the rho to be the charge density, the volume charge density. So now we consider the total charge is Q. So if we consider to calculate the E field inside this sphere, so we will have let us consider the simple case first. So when we consider the E field outside the sphere, then we draw a Gaussian surface larger than this sphere. So the total charge is Q, and it turns out to be the familiar expression. We have seen it many times. E to be K times Q over R squared for small r larger than this capital R. So for the more complicated case, if we consider the E field inside this sphere, so we draw a Gaussian surface which has a radius smaller than capital R. So this small r smaller than capital R. So now we need to consider Q enclosed, the Q enclosed, which is the charge inside this Gaussian surface, the Gaussian surface. As we assume that the charge density is uniform over the whole sphere. So actually, rho is nothing but the total charge divided the total volume, 4/3 pi r cubed, 4/3 pi r cubed. And it should also be equal to Q enclosed over 4/3 pi small r cubed, small r cubed. Because the rho should be the same for the smaller sphere and the larger sphere, for the whole sphere. So this one, these two expressions will be the same. So actually we can just cancel pi. 4/3 can also be cancelled. So we have Q enclosed. You just multiply r cubed on both sides. So we have r cubed over capital R cubed times Q. So applying the Gauss law, we have epsilon 0 EA. A is the surface area of this one, so it should be 4 pi r squared, 4 pi r squared. And Q enclosed is this one. So we substitute this expression here. And we find that r cubed can be partly cancelled with this term. So it turns out that this term remains the same, Q remains the same, but here we have small r over capital R cubed. Small r over capital R cubed. The dimension of them should be the same, because if you consider the dimension, r over r cubed, r should have a dimension L. This one should have dimension L cubed. So if you just cancel L, then it will be 1 over L squared. And actually for that one, 1 over R squared, this one should have L squared. So when you try to derive some expression, the first step is to check whether the dimension is correct. If the dimension is not correct, then there must be something wrong. Even the dimension is correct, there may be something else wrong, but at least then you can filter some of the mistakes. So actually, when you try to draw it out, for the outer one, it is inversely proportional with the R square. So it will look like this case. And for R is smaller than R, it is linearly increased. So at the center is 0. And try to increase like this. So at this point, they meet together. And then exponentially, no, not exponentially. Inversely. So inverse proportional to the R square when small r is larger than capital R. Somehow like this. If you don't really know how to use the Gauss law, you can only remember it. Maybe you may have remembered it in high school, but don't know why. Only 1 over R squared for the outside, R over capital R cubed for the inside. But now you can use the Gauss law to explain why it will be like this. So we have an additional example. This is actually the problem 11 behind in this chapter. So the volume charge density of a solid conducting sphere of radius capital R varies with radial distance r given by rho to be this case. So for this case, the rho is not uniform. It's not uniform. It is also in linear increase. This is also in linear increase. So the first question is, what is the sphere total charge? Sphere's total charge. So for this case, you can imagine the charge is not distributed uniformly. It is proportional to the radius, which means that near the center, it is very dense, and near the surface, it is much more dense. So it is proportionally increased. It has to, but this is less dense, and is almost zero near the center, and is the most dense near the surface. So we need to calculate the total charge. So actually, we need to use the triple integral. So Q would be nothing but a triple integral of the sphere rho dV, which means we have the rho, the expression of rho, and multiply the dV here. So actually, we'll use the spherical coordinate. So actually, I just mentioned yesterday for a spherical coordinate, we will have r, theta, and phi. And r, and when you consider a sphere, it should be from 0 to capital R. For theta, you can still imagine it's a polar coordinate. It will be rotating like this. So it should be from 0 to 2 pi. And for phi, it will be from negative pi to, it will be from 0 to pi. It will be 0 to pi because it only rotating like this. You have a polar coordinate. You can rotating 360 degrees, and you want to know the z-axis. So it only rotating 180 degrees. So it only has 0 to pi. So actually, we can write this as it should be. I just swap it. It should be phi and theta like this. So in this case, we should have 0 to 2 pi, 0 to pi, 0 to r. And rho, we can call this one rho s. So we have rho s times small r over capital R. And what is dV? For spherical coordinate, you may learn it later. dV is nothing but r square sine theta, dr d phi d theta. You will learn it later. For polar coordinate, if you just consider a 2D plane, so you have many circles. So if you have a dA, it will be something like a sector. So this is R, this is dr, and this is phi. So it will be something like this is d phi. So the area of this part should be dr, and this line should be r times d theta, which is the arc length. So we have r times r, dr times r d phi. So for polar coordinate, you will have r dr d phi. But for spherical coordinate, it will become r cubed times dr, which will be a volume, which will be a small volume. And you also have sine theta, d phi d theta, to specify the infinite small volume. So actually, this integration is not difficult to calculate. So it will be something like rho s over capital R, and we have 0 to r cubed dr, because we have 1 r, we have r square. So we turns out we have r cubed, and then dr. And for the next one, we have phi 0 to r 0 to pi d phi 0 to 2 pi. This one is pi. So for the next one, we should have 0 to pi sine theta d theta. So actually, all the variables can be separated. So we have dr here, d phi here, d theta here, and theta in this case. So every integration is easy to calculate. So this one is r to the 4th power over 4. This one is 2 pi. This one is nothing but 2 pi. This one will be cosine theta minus cosine theta, and then you substitute 0 and pi into it. So you will have 2 for this one. So finally, you will get the answer to be pi rho s r to the 3rd power r cubed. So you can substitute 3.14 times rho s is 35.4 times 10 to minus 12. And then r cube is 5.6 centimeter, which is 0.056 to the 3rd power. So it turns out to be 1.95 femtocoulomb. So don't be too worried about that. It's just to show you what you can use calculus to solve a physics problem. Actually, the selected problem or the exam will not be so difficult at this.